So I want to have out this handout because we're still wrapping up the calculations. We've done page 1, 2. How far did we get? We are on number 7. Oh, doing eta squared. That's what we're doing. We're calculating effect size. Okay, so we made it all the way through here. So we did Q, we did HSD critical. We did all. We've done all of that, so now we're here on eta squared. Now, eta squared, which is our measure of effect size for analysis of variance, is related to R squared. It's a form of R squared, or they're forms of the same kind of statistic. And what that means is that we use the same evaluation table for eta squared that we use for R squared. They're exactly the same. It also means we convert decimals to percentages, just like we did with R squared, so we treat them as the same thing. Now, the formula for calculating eta squared for an independent group's analysis of variance is the sum of squares between conditions over the sum of squares between conditions plus the sum of squares within conditions. Now, these values are values that we had to calculate in order to be able to perform our F-test. So you just want to look back in your handout, on your worksheet, look back to that table where we calculated sum of squares between conditions, sum of squares within conditions, sum of squares total, degrees of freedom between conditions, degrees of freedom within conditions, degrees of freedom total, and then where we got those values so we could calculate our mean squares between conditions and mean square within conditions. So if we look back there in our worksheet, did you find those numbers? Okay. What's our sum of squares between conditions for this analysis?
43.33.
43.33. Okay. So we're going to substitute that in here. And what was our sum of squares within conditions?
34.
34? Okay. So now we do this math. We're going to do 43.33 divided by 77.33. Is that right?
Yes.
Okay. So 43.33 divided by 77.33. And what do we get? Hmm? 0.56. I have a vote for 0.56. I see some agreement with 0.56. Okay, so that is going to be 56% is going to be our eta squared. And if we think back to what we know about R squared, is that a small, medium, or large effect? Large, definitely large, right? So that's a large effect. Now we need to summarize our findings and summarize them in words as well as in APA style. So to do this, let me fill this back out again because this will help us talk about what we actually found. Can you guys tell me our HSD critical again? 2.83. And what was my absolute value of the difference between mean 1 and mean 2? 3. And between mean 1 and mean 3?
4.
And between mean 2 and mean 3?
4.
1. And so now let's practice doing the evaluation again. Is this difference significant?
Yes.
The first one? Yes. How do we know that? That's right. This value is greater than our HSD critical, so it's significant. What about this one? Next one. Yes, that one's significant too. And what about the last one? No. All right. So tell me again, we've rejected the null hypothesis. So we know that the length of time that patients stay in the hospital is influenced by their diagnosis. And what groups are we comparing again? People with affective disorders, people with cognitive disorders, and people with drug-related conditions. So we know that whether a patient is diagnosed with an affective disorder, a cognitive disorder, or a drug-related condition, it will influence how long they stay in the hospital. There are significant differences in the length of stay for members of those three groups. Who's different? Okay, we know by looking at this value here, this comparison between mean 1 and mean 2. We're comparing mean 1, that's for our affective disorders. Mean 2, that's for cognitive disorders. Mean 3, that's for people with drug-related conditions. Okay? So we know that mean 1 and mean 2 are significantly different from each other. That means that patients with affective disorders stay in the hospital a significantly shorter period of time than patients with cognitive disorders. How do I know it's a shorter period of time? No, we're thinking about the mean for group 1 and the mean for group 2. Where are those numbers?
Here it's Q, right?
No, where are the means? We'll just pick random names. Yeah, no. Where are the means?
Outside of our curriculum. The mean.
They're on the first page of your handout. Turn to the first page of your handout and take a look. Right? The means for each group, the things we're actually comparing. How long do people with affective disorders stay in the hospital? On average? 6 weeks. How long do people with cognitive disorders stay in the hospital on average? 9 weeks. How long do people with drug-related conditions stay in the hospital on average? 10 weeks. So what we know looking at these comparisons up here is that 6 weeks is significantly less than 9 weeks. We also know from this second comparison that 6 weeks is significantly less than 10 weeks. And from this third comparison, we know that 9 weeks is not significantly different from 10 weeks. So if we convert that into a statement, we can say that patients with affective disorders stay in the hospital a significantly shorter period of time than either patients with cognitive disorders or those with drug-related conditions. However, there is no difference in how long patients with cognitive disorders and those with drug-related conditions stay in the hospital. Does that make sense? Question?
What was the last part of that?
Which part?
However.
However. Okay. So the first statement I said, patients with affective disorders stay in the hospital a significantly shorter period of time than patients with cognitive disorders. That's what this 3 means. Patients with affective disorders also stay in the hospital a significantly shorter period of time than those with cognitive disorders. That's what this 4 means. Our last number is a 1. It's not significant. So what does it mean? Who are we comparing to? Go ahead.
So there is no significance in difference between cognitive disorders, stay, and drug-related conditions.
Right, so there's no difference in length of stay for patients with cognitive disorders and those with drug-related conditions. So each one of those statements that I made is describing what one of these comparisons means. Does that make sense? So overall, we can say we rejected the null hypothesis. There was a significant difference in the length of stay for patients, depending on their diagnosis. Patients with affective disorders stayed in the hospital a significantly shorter period of time than those with cognitive disorders or drug-related conditions. However, there was no difference in length of stay for patients with cognitive disorders and drug-related conditions. Yes?
For the exam, are you going to asks us to hit each of those points? Like, can we just, because for the first statement you made, you said that there's a significant difference between patients with affective disorder and patients with cognitive disorder. And then you said, however, there's no significant difference between...
So I want your summary to accurately describe in words all of these results. And the first statement I made when I said there is a significant difference in the length of stay depending on the patient's diagnosis. That's actually a summary of the findings from the F test, because we got a significant F value when we did the ANOVA. And I'm saying there's a significant difference. Then when I say specifically, what I'm doing is I'm going in and actually describing the results of the post hoc test. Now, you can be more brief. You could say patients with affective disorders stay in the hospital a significantly shorter period of time than either those with cognitive disorders or drug-related conditions. And that would summarize both of these numbers in one sentence. So you can be brief in that way. But when people have a lot of things to summarize, I find that sometimes it's helpful if you just try to describe each thing in one sentence so you make sure you're hitting all the points. The more you practice, the easier it will be for you to be more brief and more concise. But whichever way you do it, as long as you hit all the points and make it clear what the entire pattern of results was, I'm happy. All right, any questions about that description before we do the summary in APA style? Okay. When we do APA style statement, let me erase this and move it up so we have something to look right. When we summarize a statement in APA style for an ANOVA, summarize APA style, we start with the test, F. Then, in parentheses, we use the degrees of freedom we use to look up the critical value. For an independent group ANOVA, that's degrees of freedom between conditions and degrees of freedom within conditions. So what was my degrees of freedom between conditions for this analysis?
2 and 12. 2 and 12.
2 and 12. So that's between conditions, and within conditions was 12. Then we put our observed value. What was our observed value for F?
7.66.
7.66. And then P is less than our alpha, which was 0.05, because we got a significant result. Our eta squared was 56%. And our HSD critical was 2.83. So what you have to put in order is listed on your worksheet. And all we're doing now is plugging in the values from this particular analysis.
Do you still have to put the positive for the...
You don't have to, because F values are always positive.
Oh.
There's no such thing as a negative F value.
Right.
If you ever get a negative F value, something is horribly wrong. Because F is calculated from squared values. So it should be positive. Always positive. And the closer F observed gets to 1, the less likely you are to get a significant result. If F is 1, you absolutely have no significance. So F has to get away from 1. All right. Any questions about that before we move on to the related groups analysis? No? Okay, now we're going to move on to an analysis on related groups. And for this, we're changing it up a little bit. We're going to look at a group of 5 children, Dan, Diana, Kelly, Kim, and Linda. And we're going to measure them at 3 different points in time. and 28 days. What we're going to have them do over the course of those 28 days is practice reading out loud to a caregiver to see if it improves how well they read. So we're measuring the number of errors they make when they read out loud, and we're doing it, taking a baseline measure at 0 days, letting them practice at home for 2 weeks, then come into the lab, have them read a story and count how many mistakes they made, then have them go home, practice for another 2 weeks, come back in, have them read a new story, and see how many mistakes they made. I've given you their number of scores, their number of errors for each point in time. I've also given you some basic descriptive statistics so you don't have to calculate those, because now I think you know how to get in degrees of freedom, the mean, and sum of squares. I'm not worried about having you calculate those this time. What is the null hypothesis for this study? If you ever miss class, you can always get it online. Materials are online. What's my null hypothesis?
But there won't be any change in the number of errors that the children make over days of practice.
That's right. So we want to make sure we name each one of the days of practice, so there will be no difference in the number of errors children make between 0 days, 14 days, and 28 days of practice. Okay, make sure you name all the groups. There will be no difference in the number of errors children make between 0 days, 14 days, and 28 days of practice. What's the alternate hypothesis going to be?
There will be a difference.
There will be a difference what?
In the number of errors children make between 0 to 14 and 20.
There you go. There will be a difference in the number of errors that children make when reading out loud after 0 days, 14 days, and 28 days of practice.
Do we need to say, because it says that she predicts that children will reduce the number of errors, do we need to say something about the direction?
So you could, if you wanted to say for the alternate hypothesis that there will be a reduction in the number of errors that children make between 0 days, 14 days, and 28 days of practice. You could say that. That'd be fine. What we don't know is if there's a couple different ways we could get a reduction and still support the researcher's hypothesis. It could be that we see a reduction that's linear, so they go down consistently. So 14 days is less than 0 days, 28 days is less than 14 days, that's possible. Could also be that it takes kids a little bit of time to show any improvement. So maybe there's no difference between 0 days and 14 days, but then we do see a reduction between 14 and 28 days. That would be correct. It's also possible that children get better between 0 days and 14 days, and then at that point they level off and there's no difference after that, right? All of those would support the hypothesis. Okay, now, the first calculations you need to make are t squared over n, and the sum of x squared. So these are all exactly the same calculations as we did last time. So what I like to do is like to have people in the front row do 0 days, people in the second row do 14 days, people in the back row do 28 days. Calculate t squared over n, and the sum of x squared for your group. And if you finish, for your group, you can go ahead and do it for the other group just to see if you can get the same numbers as the other people who are covering that group. No, but you can look on hers. Well, this is the worksheet from last time, so. If you don't have the numbers, there, you can write it down for your group. All right. We doing okay? You guys have a question? You guys are in the middle row, right? You're doing 14 days. You guys are doing 14 days. You're in the second row. Middle row, 0 days, 14 days, 28 days. That's okay, it doesn't matter. You can do multiple rows. Yeah.
How did we, I think, because I missed the first day, and I didn't have a chance to go back and watch it. How do we
let's see here. Do you have this worksheet right here?
This is the day that I missed, and except for the day that I wasn't here.
Yeah, it's just right here. It tells you, here actually. So T is pretty much the sum of all these, of all the X's for that condition.
Anybody have any
You
questions?
just add all this, you get T. So
Questions? How will you do?
try that
Yes.
first.
It's not EX squared. The sum of X squared. Remember, this is where we square each value and then add them up.
And then you just square it there.
Square each value and then add them up. So.
Oh, okay, so we square one of each side.
Yeah, you square these, so 8 squared, 5 squared, 5 squared, 7 squared, 5 squared, and then you add those up. I know, that's right, that's how we're doing it again.
Okay, 64.
Yep.
The far, okay, cool. And then you just square them all and add them up. So
Yeah,
it's
you know how to do that, yeah.
Questions? You got it? Huh? What's your question?
For the sum,
Of X squared?
That's what I got.
You have to square each of the values for your
It's the
condition.
same exact things.
So you
You know.
square, if you're doing 14, you have to square 3, square 3, square 0, square 2, square 2, and then add up the squared values.
Yeah, they're pretty much the same from the beginning.
All right. You got it? You guys have a T value for 0 days?
30.
30. We have a T value for 14 days?
10.
10. T value for 28 days? T value for 28 days? 5. T squared for 0 days?
900.
900. T squared for 14 days? 100. T squared for 28 days? 25?
I mean, aren't you just multiplying it twice?
Yeah. That's why everyone should be shouting out the answer, because it's very straightforward. 5 times 5.
25.
There we go. Yeah. The silence, as I just said, like T squared. It's like, you know this. Do it. Okay. T squared over N for 0 days? 180. T squared over N for 14 days? 20. There. And T squared over N for 28 days?
5.
5. All right. And here's the hard one, right? Sum of X squared. This is where you have to square each of the values in your condition and then add up those squared values.
188.
188 for 0 days? Yes? Okay. And then for 14 days? 26. And for 28 days? 7? The squared values are 7?
Yeah. I mean, I have the printout.
1 squared, yeah. That's so weird to see a squared out of it.
For independent.
Okay, so we've got
Yeah, but-
all of these numbers. Does anybody have any questions where these numbers came from?
Is this one mine?
How much are
No.
Oh, I just had mine.
Everything, every single step. I want every single step written out. I want the formula and every single step.
No,
I want to know,
it's just all-
even for the easy
I was
stuff.
saying-
You're like, oh, it's
It's
super
all there.
easy. If you write that, you know, I want you to make it very clear exactly how you got from the data I gave you to the numbers you write down in the blanks. Write your formulas, write every step. Because what I often find is that when people don't write down all their steps, they skip a step. They forget a square root, or they forget to divide by something, or they divide by n when they should have divided by degrees of freedom, or vice versa. So write everything down so I can see exactly what you're thinking, exactly the steps you're going through, in case there are errors.
I think this is yours.
Okay.
Okay. Any questions about this? You guys know where all these values came from? Okay. Now, we're going to skip step 3 just for a second, because I want to show you that if you go to step 4a, this step right here, you know how to calculate most of these values too. You know how to calculate everything here except that one. Okay. This is that stage where we start doing the pooling, right? So far we haven't done anything new. No new formulas compared to independent groups ANOVA. All exactly the same up to this point. So where do I get G? Where does G come from?
Well, so all that.
Sum of all the big T's, right? So if I add up all those big T's, what do I get? G is the sum of all the T's. 45? Big N, that's the sum of all the little n's. So that's 5 plus 5 plus 5, so that's 15. If I calculate G squared over big N, what do I get? Squared G and then divide by big N. I have a vote for 135. 135. 135. The sum of x squared all. This is where we're pooling, right? You're just going to add all of the sum of x squared values from the first page, where we calculated it for each condition. You're just going to add those together. I have a vote for 221. I see nods. Yes, 221. And what about the sum of t squared over n? That's where you just go to that front page where you calculated t squared over n for each condition and add those all together.
205.
I have a vote for 205. Nod for 205, 205. Okay? All right. Does anyone have any questions about where any of those numbers came from? Nope, that was just a timely stretch. Or she was cheering because she got them all right. Touchdown! Homecoming! Okay. All right, so we have those numbers. Now, this last number here, sum of p squared over k, we haven't done that before. Okay? And we won't be able to do that until we do an additional set of calculations. This is the first new calculation we've done since we started doing this ANOVA. All of the steps we've done so far are exactly the same for independent groups ANOVA and related groups ANOVA. I'm going to get rid of this now so I can move down. And before we can calculate the sum of p squared over k, we've got to figure out what p is. Okay? And I will tell you that p is the sum of x for a given participant. That's different than big T, which was the sum of x for a given condition. So to calculate T, before I added up the scores, I would get a T for 0 days and a T for 14 days and a T for 28 days, because that's for conditions. But P is for participants. So now I need a P value for Dan and a P value for Diana and a P value for Kelly, a P value for Kim, and a P value for Linda. And all I have to do is add up the scores for each subject. Okay? So for Dan, I'm going to add 8 plus 3 plus 1 to get his p-score. What's his p-score?
12.
12. And Diana? What's her score?
8.
Kelly? 6. Kim?
11.
And Linda?
8.
8. Now I just need to square each of those scores. I know what I'm shooting for is something called sum of p squared over k. That means I'm going to have to square all these p's. All right, so if I square 12, what do I get? 144. And if I square 8, what do I get? And 6? And 11? And 8? 64. Good. Now, what is my k again? What's k? The number of conditions, right, or number of treatments. So how many conditions do I have in this analysis? 3, right? 0 days, 14 days, and 28 days. So k is 3, so I'm going to divide the number I just calculated by 3. So what is 144 divided by 3? 48. And 64 divided by? What?
21.3.
21 point, is that to 2 decimal places? 33. 21.33, okay? And 36 divided by 3? 121 divided by 3? 40.33. And 64 divided by 3, we said, was 21.33 already. Okay. So this calculation is clearly giving us some information about the participants. I'm going to show you in a minute exactly what information that is. Does everybody understand where these values came from? P is just the sum of x for a given participant, and then we square that value and then divide it by k, which is the number of scores that went into the number. Right? Okay. Everyone have those numbers written down? And you know where they came from. Okay. Now we're going to come down here. And our chart is a little bit bigger than it was before. Last time, we didn't have this condition, we didn't have this condition, we didn't have this, we didn't have this, we didn't have this, but we did have sum of squares between conditions, degrees of freedom between conditions, mean square between conditions, sum of squares and degrees of freedom within conditions, sum of squares and degrees of freedom total. We had those before, right? Okay. Do you guys remember how to get those values? Because they're exactly the same as for independent groups ANOVA. What's the formula for calculating sum of squares between conditions? Do you remember? Can you find it?
Sum squares between conditions, or sum of t squared over minus g squared over.
Okay, so if you wrote out on your notes, remember I asked you in your notes last time to write a grid on your paper that had the formula in each box? Can you find that in your notes? Okay, so the formula for this box, for the sum of squares between conditions, is the sum of t squared over n minus g squared over big N. Okay, so all you have to do now is look up above on the worksheet, find out what that sum of t squared over n was, because you wrote it in the box, and then subtract out g squared over big N, which you also wrote in the box. What was our sum of t squared over n? 205. And what was our g squared over big N? 135. So what's the difference? $70. 70? Okay, so write that in the box. How did I calculate the sum of squares within conditions?
The sum of SS conditions?
That's right. So if we say the sum of squares for all conditions, what does that mean? Basically, yeah, this is like pooled sum of squares. So what do? Go to the front page. Look at the data you were provided where you have the sum of squares for each condition and add those sums of squares together. This is just sum of squares pooled. But now for more than two conditions. So if I add up the sums of squares from the first page, what do I get?
16.
16? And what's my formula? And give me the hard one first. What's my formula for calculating sum of squares total? Sum of x squared minus g squared over big N. Right. So if I calculate that, what do I get? Sum of x squared all minus g squared over big N. 86. And then how do I check it to make sure that my math is good so far? What's my checking formula? It's the easy one. Right. I check it by seeing if it equals those two added together. And if those don't match, something has gone wrong up to this point. You need to go back and check your work. If they do match, then chances are you're good up to this point. You haven't made any mistakes. Right? How do I get degrees of freedom between conditions? K minus 1. All right, so K we decided already was 3. So 3 minus 1, 2. And how do I get my degrees of freedom within conditions?
N minus K.
Big N minus K. Yeah. And we already decided big N is what? 15. And we just said that K is 3, so 15 minus 3, 12. And to get the total, degrees of freedom total, big N minus 1. So that's 15 minus 1, 14. And I also have a double check formula for that, which is, not surprisingly, degrees of freedom between conditions plus degrees of freedom within conditions. And again, if both of those match, so 3 plus 12 is also 14. If both of those match, you're probably doing okay so far. If they don't match, if the output of these two formulas doesn't match, something's gone wrong somewhere. Now the last one up there that we learned how to do before is mean square between conditions. How do I calculate that? It's a form of sample variance, remember I told you?
So it's between conditions over degrees of freedom between conditions.
That's right. Sum of squares between conditions over degrees of freedom between conditions. And there's a visual cue here, right? It's just this box over that box. So 70 divided by 2? 35. Okay. So all of those calculations, all of them, exactly the same for both ANOVA. So if you missed last time, you just learned what we did last time. Yay! Okay. So we've got everything we've done, with the exception of P, and the P squared over K thing, is exactly the same as last time. Now let's talk about these other boxes, these new boxes. Now to understand what we're doing here, you need to keep in mind that an independent group's ANOVA is designed assuming that there are different subjects in each condition, which is true. The ANOVA expects there to be different subjects in each condition. And that's what ANOVA was originally designed to do. Find out about differences in between subject studies. When they decided that they wanted to also be able to do statistical analysis on within subject studies, they just took the ANOVA that they had designed for between subjects and basically threw in a patch. They threw in a modification. That modification is intended to adjust the formula so that it doesn't assume there are different subjects in every condition. Because in a within subjects design, the same subjects experience each condition, right? It's just the same subjects getting tested over and over and over. So there's less variance. There's less variability because there are fewer individual differences in the study. We don't have to worry about the subjects in group 1 being different from the subjects in group 2 being different than the subjects in group 3. We don't have to worry about that because it's the same subjects in group 1, group 2, and group 3. Same people, just doing different stuff. So the calculations we're going to do right now are to make that adjustment. Basically, to suck out the extra variance that would have occurred if we had different subjects in every condition. So we're doing an adjustment, a patch, if you want to think about it. We're repairing the formula so that it will work better for the kind of study we're doing. Give us more accurate information. So we're going to calculate now a sum of squares between subjects and a degrees of freedom between subjects. And we all know sum of squares over degrees of freedom is sample variance, right? It's a kind of sample variance. So we're basically getting information about variance that would come from having different subjects in every condition. And we're going to subtract it out of the values that we've already calculated. Okay. To get sum of squares between subjects, you take the sum of p squared over k minus g squared over big N. So what did we get for the sum of p squared over k? What did you say?
42.99.
Just 42.99?
142.
142. 142.99 was our sum of p squared over k. And what was our g squared over big N? 135. Okay, so if we do that math, what do we get for the sum of squares between subjects? $7.99. And the degrees of freedom between subjects is calculated using our all-time favorite degrees of freedom formula, little n minus 1. Little n minus 1. And what's little n? How many subjects do we have in our study? 5. 5 minus 1. 4. So now that we have our adjustment values, we're going to do the adjustment. And here's how we do that. We subtract the between subjects information from the within conditions information. Right? Because within conditions, this is what's telling us about what's happening inside each group, the variance inside each group. And now we only have one group instead of lots of different groups. So we're basically going to clean it up to make it reflect the fact that we've only got one group, not multiple groups of subjects. So I'm going to take 16 and subtract 7.99. What do I get? 8.01. And I'm going to take 12 and subtract 4. What do I get? Vote for 8. So if you want to think of it this way, it's just like that. And if I take 8.01 and divide it by 8, what do I get? One. Hit 1. Okay? So now we've got the adjusted value that we need for our denominator. We fixed the value for the denominator, for the F ratio, and now we can calculate F observed. So for the related groups ANOVA, F observed is mean square between conditions over mean square error. Question?
How did you get 4?
4, I use the formula for degrees of freedom between subjects, which is little n minus 1. Question? I don't want to move on until everybody knows where every value came from. Do you have a question? You got it? You got it? So, just like last time, I want to focus your attention on the mean square values we calculated. Notice there's nothing here, nothing here, nothing here. That's because we don't need any of those values, so you're not calculating them. Please, 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 on the test. If you get boxes that look like this, do not go in and draw these in and do the math for those boxes. Students do it every semester. And I'm like, you don't need them. That's why I didn't put a box there. Don't spend your time doing stuff like that. And if you're like, oh, but I do need those values, then something's wrong with your formula card, because we don't need any of these values for this particular ANOVA. Okay? I won't put blank boxes there and then make you guess which ones you need. If you get this ANOVA on your test, you're going to have boxes that look just like that. And you'll fill them in just like that. All right, so if my mean square between conditions is 35 and my mean squared error is 1, that means my F observed is 35. Now, we have to look up our critical value. And you'll recall, to do that, let me move this for a second. To look up values on the F distribution table, we need to have a degrees of freedom denominator and a degrees of freedom numerator. And you have to know which one is which for the ANOVA that you're doing. For independent groups, the degrees of freedom numerator is what? What did we use last time for degrees of freedom numerator?
MSBC?
Not MS. We're looking for a degrees of freedom. Degrees of freedom what? Yes. And what's my degrees of freedom denominator for independent groups? What did we use last time?
Yeah, for error terms. The degrees of freedom for error terms.
No, here we're looking for the one for, well, it is the error term, it's the denominator, but to be clear, what degrees of freedom did we use for independent samples? What do we call it? What's its name? Within conditions. Degrees of freedom within conditions. Okay, that's what we used last time. And the reason we used that last time is because to calculate F observed, for independent groups, we use mean square between conditions over mean square within conditions. Between conditions is in the numerator, within conditions is in the denominator. So we use whatever degrees of freedom corresponds with that part of our F ratio. Now, for related groups, our F ratio is calculated differently. We have mean square between conditions over mean square error. So now, when we look up our degrees of freedom numerator, what are we going to use? What degrees of freedom? Between conditions, right? So that's going to be the same. Because between conditions, between conditions. It's the same because the numerators are the same for those two formulas. Right? And what about my degrees of freedom denominator? What am I going to use now? These aren't the same, which means that's going to change. What am I going to use?
Mean square error.
Well, mean square error is the denominator here. What degrees of freedom am I going to use?
Degrees of freedom error.
Degrees of freedom error, right. So when I look up my critical value for related groups ANOVA, I'm going to use across the top for degrees of freedom numerator, whatever I had for degrees of freedom between conditions. And down the side, when it asks for degrees of freedom denominator, I'm going to use whatever I had for degrees of freedom error. And if you use the wrong set, you're going to get the wrong critical value. Because the denominators are different. So what was our degrees of freedom between conditions for this study?
Was it 2?
I don't know, was it? It's 2. 2. Okay, so it's 2. Right? And what's our degrees of freedom error for this study? 8. So I'm going to go up here, go to 2, across the top, and then down to 8. And I'm going to look to see, so here are my options, and I'm going to look to see which one is in light phase type, because our alpha is 0.05. And what do we get?
5.32.
8. We're looking.
Oh, sorry.
Remember, we have degrees of freedom numerator is 2. So what do we get?
4.46.
4.46. So our critical value is 4.46. So we know that our F critical is 35. Oh, our F critical is 4.46. Our F observed is 35. So am I going to reject or retain the null hypothesis? Reject. Yeah, because 36 is much more extreme than 4.46. Much more extreme. So I'm rejecting the null hypothesis. Now I'm going to do my effect size and my post hoc tests. All right, let's do the post hoc test first. All right, so what I need to look up Q. How do I look up Q again? What do I need? That's on the very back of your packet of critical values, right? It's that oddly named studentized range statistic, Q. And it says I need to know K for the number of treatments And then I need to know degrees of freedom for the error term. What does that mean again? Degrees of freedom for the error term is another way to say what? Degrees of freedom denominator. Okay. Degrees of freedom for the error term is the same thing as degrees of freedom denominator. So K is number of treatments. That was how many? 3. And the degrees of freedom for our error term was? So our degrees of freedom denominator was? 8. Okay. So I go 3 down to 8, and I'm looking for the number in light phase type, and what is that? 4.04. Okay. So Q is going to be 4.04. Now we have to calculate HSE critical. And the formula for HSE critical for related groups ANOVA is a little bit different than the one for independent groups ANOVA. Okay? Still has Q in front. Still has a square root. Still has N there. But here in this numerator slot, instead of mean square within conditions, it's got mean squared error. We never use mean square within conditions when we do a related groups ANOVA. Any place we would use it, we substitute in mean square error, because that's the adjusted value. That's the fixed value that's been cleaned up, where we pulled out that individual differences variance. So I know my Q is 4.04. My mean square error was 1, right? Mean square error was 1. My small n for this study is 5. So I'm doing 4.04 times the square root of 0.20. What's the square root of 0.2? Okay, if I take 4.04 times 0.45, what do I get? $1.82? Yes, 1.82. 4.04 times 0.45 is 1.82. All right. So this is 4.04. You guys said this is 1.82. That means that's the value B. If any two of our means are more different than that value, then that comparison is statistically significant. If any of our comparisons have a difference that's less than that value, then those two groups are not different from each other. So let's go back now. We have to go look at the means again. What's our mean? Our mean 1. That's our mean for 0 days, right? That's for 0 days. 0 days. How many errors on average did the kids make at 0 days? 6? Okay, on average they made 6 errors. What about the mean for group 2? That's our kids at 14 days. How many errors did they make on average after 14 days? 2. And how many errors did our kids make on average after 28 days? 1. So now what we're going to do is we're going to do those planned comparisons. We're going to compare 0 and 14, 0 and 28, and 14 and 28. Okay, we're going to compare each pair of means. And we're going to see how different they are, and see if they're different enough for it to be significant. So first we're going to do mean 1 and mean 2. What's the difference between mean 1 and mean 2? 4. Is 4 bigger than 1.82? Yes. So that means that this difference is significant. Children made significantly fewer errors after 14 days than they did at the beginning of the study. Okay. 2 is significantly less than 6 for these data. All right, so the next comparison is going to be mean 1 and mean 3. So now we're comparing 6 and 1. And what's the difference between those two? 5. Is 5 bigger than 1.82? Yes. So that means that the children made significantly fewer errors after 28 days than they did at the beginning of the study. 1 is significantly smaller than 6 for these data. And the last comparison we're going to do is group 2 and group 3. So we look at mean 2, mean 3. The difference between 2 and 1 is 1. Is 1 bigger than 1.82? No. So this is not significant. Not significant. That means that there was no difference in the number of errors the kids made between 14 days and 28 days. No significant difference. This difference of 1 error is not meaningful. So, do you get that pattern? Do you see where those descriptions came from? We can say, we know that we had a significant difference. That's what our F-test told us. Our F-test told us that the number of days children practice has a significant effect on how many errors they make when reading out loud. Now we know exactly what that effect is, what it looks like. Children make significantly fewer errors after 14 days of practice and after 28 days of practice than they did after 0 days of practice. 14 days of practice, significant effect. 28 days of practice, significant effect, compared to 0 days of practice. However, there's no difference in the number of errors they make between 14 days and 28 days. So these extra 2 weeks of practice don't do them any extra good. They get as good as they're going to get, basically, in the first 2 weeks. But part of that is because what we're talking about here is a floor effect. They can't really get much better. Everybody's going to make a mistake now and then. So it's hard for them to get much better than they already are after 2 weeks. Okay, let's talk about effect size. Now, if we think back to the formula we used earlier for independent groups, ANOVA, when we calculated eta squared, we use this formula. Sum of squares between conditions over sum of squares between conditions plus sum of squares within conditions. That's what we did last time, right? That's what we did for independent groups. We don't ever use within condition stuff if we can help it for related groups. Because this value here has too much variance in it. It assumes that the subjects in our study are different for each condition, and they're not. So we need to clean up this second number. And we're going to do that by subtracting out sum of squares between subjects. Now, if you have your handout that has the formulas for one-way analysis of variance on related subjects. If you have your handout, you look on the back page under step 12, and it says calculate effect size with eta square. There's actually a typo on the handout, and I want you to fix it right now. I'm going to show you how to fix it. Here's what the formula should look like. It says sum of squares, the second part of the formula, it says sum of squares between conditions over sum of squares between conditions minus sum of squared error. I should say plus sum of squared error. So just change that minus to a plus. And that's because these two together are sum of squared error. All right, so our sum of squares between conditions was what? What was our sum of squares between conditions? Sum of squares between conditions?
Oh,
70. And what was our sum of squares error? 8.01. So that gives us 70 over 78.01. Huh? Oh, typo again. That's good. Means you know what you're doing. And my brain is full. All right. I wrote the right number over here. I knew what I meant. I meant plus. I wrote minus. All right. So 70 over 78.01. What do you get? 0.9. Okay. So equals 0.9 or 90%. Okay. Is that a small, medium, or large effect? Large. Incredibly large. Ginormously large. Right? Definitely large. All right. Does anybody have any questions about where any of those numbers came from? No? We're good? Okay. All right, so now we're going to write out our APA style statistical statement and summarize in words what happened. So we already said there is a significant difference in the number of errors children make when reading out loud between 0 days, 14 days, and 28 days of practice. Specifically, children make significantly fewer errors after 14 days of practice and 28 days of practice. However, there's no difference in the number of errors they make between 14 days and 28 days of practice. Right? Is that right? Does that make sense? That's what we said before? You understood what that meant? And how we got to that conclusion? So now I need to write out APA style. First thing is going to be F. Then I'm going to put the degrees of freedom that I use to look up my critical value. And for related groups ANOVA, that's degrees of freedom between conditions and degrees of freedom error. So my degrees of freedom between conditions was what? 2. And my degrees of freedom error was?
4.
Degrees of freedom error? 8. My observed value was 35. P is less than 0.05 because we got a significant result, and our alpha was 0.05. Our eta squared was 90%. And then lastly, we put our HSD critical, and what was that? 1.82.